Welcome to this course on power electronics. This course is essentially the study of operation and performance of certain electrical circuits known as power electronic converters, which are used in different applications. Let us try to take a look at the different applications of power electronic converters. A few of the applications are illustrated in this slide. Power electronic converters are used for long distance power transmission at high voltage DC. They are also used to improve the power quality in power systems. What do we mean by power quality? It is primarily concerned about the non-sinusoidal nature of voltages and the reactive power in transmission and distribution systems. We will learn about power quality in this course to some extent. The power converters are used in motor drives and in robots for numerous industrial applications. The uninterruptible power supplies and the chargers for mobile phones and laptops, which we use in our day-to-day life, have power electronic converters as their basic building blocks. Electric vehicles also employ power electronic converters for charge control of their batteries and for speed or torque control of their motors. Power electronic converters are inevitable to interface renewable energy sources such as photovoltaic arrays or wind turbines to the utility. Electric traction is widely used in many countries, and the locomotives or trains have a variety of power converters on board. The power electronic converters are also used in LED lighting. Thus, a wide range of applications employ power electronic converters. But why do we need these converters? It is because of the fact that electrical energy needs to be available at different levels of voltage and current. The voltage levels are usually fixed, while the current levels are determined by the impedance of loads in most cases. Here are some voltage levels needed from the user perspective in both domestic and industrial applications. That means an equipment at the user end needs electrical energy to be supplied at a prescribed voltage. For example, consider a cell phone battery, which typically works on 5 volt DC. But the voltage available at our home is single phase 230 volts 50 Hz AC. What is this 230 volts? It is the root mean square value of the sinusoidally varying AC voltage. If we want to charge our phone, we need to apply 5 volt DC to the phone's battery. So we need a device which converts the single phase 230 volts 50 Hz AC to 5 volt DC, which is a power electronic circuit or converter, and that is nothing but our cell phone charger. You can take a look at the input and output specifications of your phone charger, which are usually printed on its casing. Similarly, we have other alkaline batteries of AA or AAA size. There is even a quad A size, which are rated at 1.5 volt DC. Some rectangular batteries are rated for 9 volt DC. The motherboard of a computer works typically on 3 kinds of power supplies: plus 5 volts, plus 3.3 volts, and plus or minus 12 volts. All of them are DC. How do we understand plus or minus 12 volts? It means that there are 3 supply wires. One of them is at zero potential, known as ground. With reference to this ground wire, one of the other 2 wires is at positive 12 volts, while the remaining third wire is at negative 12 volts. Then we have many motors in domestic appliances: dryers, compressors, mixers, grinders, blenders, washing machines, etc. All of them need to work with single phase 230 volts 50 Hz, and sometimes the magnitude of AC voltage and frequency at the motor terminals need to be variable. Motors in industrial applications typically work with 3-phase voltages rated at 415 volts all the way up to 6600 volts and 50 Hz. However, the magnitude and frequency of these voltages also need to be varied depending upon the application. Please note that the 3-phase voltage mentioned here is the RMS value of line-to-line voltage. The telecom power supply usually works on 48 volts DC. Auxiliary systems of a conventional automotive need 12 volts or 24 volts or 48 volt DC. If we consider EV batteries, they typically operate at DC voltages of 48 volts or 72 volts. Mahindra E2O has 48 volts or 72 volts variants. But the motor in an electric vehicle might need a 3-phase variable AC. Coming to electric traction, there are different levels of voltage needed. 3-phase 2.2 kV is needed for the propulsion motors, 3-phase 415 volts is needed for the auxiliary motors, and single-phase 110 volt supply is needed for lighting, charging points, etc. The power supply system in an aircraft typically involves 115 volts or 230 volts, 400 Hz AC and 28 volt DC. Having known the voltage levels from the user side, let us have a look at the different voltage levels from the source side. The synchronous generators or alternators in power plants typically generate 3-phase voltages at 6.6 kV, 11 kV or 13.8 kV. AC power transmission usually happens at 400 kV, 132 kV or 33 kV. The power distribution network typically has a voltage of 11 kV. From the 11 kV distribution network, the industrial customers receive power at 415 volts or 440 volts. The domestic power supply is single phase 230 volts. Except for this domestic single phase power supply, all the above voltages are 3-phase voltages, right from whether it be 6.6 kV, 11 kV, 13.8 kV, 400, 132, they are all 3-phase voltages, and the voltage levels indicated are RMS line to line voltages. And the frequency of generation, transmission and distribution is all rated at 50 Hz. So transformers are used to step up or step down the voltage magnitude in power transmission and distribution. However, long distance power transmission happens at high voltage DC in some cases, typically at voltage levels of 500 kV and 765 kV DC. So these DC voltages have to be interfaced with the 3-phase AC grid. That brings in the need of power electronic converters in power transmission systems. Besides the conventional energy sources, we have some renewable sources in our power system. Wind turbine generators among the renewable sources typically generate 3-phase AC voltages ranging from 690 volts to 3.3 kV. One distinctive feature of the wind turbine generators is that they generate AC voltages of variable frequency. Why? The frequency of generation typically depends upon the speed of rotation. So the speed of rotation could be decided by the wind speed, so which is unpredictable. Yeah, it can be predicted, but then it is not controllable. So the frequency of generation keeps varying, while we need to interface these generators with our fixed frequency grid. So power electronic converters are needed for this purpose. Similarly, we have photovoltaic arrays or panels usually operating at 30 volts to 50 volts DC, and fuel cell stacks operating at 200 volts to 300 volt DC. These energy sources also have to be interfaced with AC utility or AC loads. What do we understand from these examples? We understand that there is a lot of dissimilarity among the sources and the loads in terms of voltage levels. Therefore, we need an equipment which serves as an interface between the sources and the loads, and that interfacing is accomplished by power electronic converters. In other words, we need power electronic converters to facilitate the flow of electrical energy from one voltage or current or frequency level to the other. The process of energy flow in a power converter is referred to as power conversion. So with that introduction, let us have a look at the course structure. This course is divided into 6 modules. We'll learn the fundamentals of power conversion in the first module. Based on the voltage levels we discussed previously, the power converters can be broadly classified into 4 categories. It could be AC to AC converters, DC to DC converters, DC to AC, and AC to AC converters. The remaining modules of the course have been structured based on the type of power conversion. As you can see, separate modules or submodules are devoted to discussion on switches. This hints at the fact that switches are the most important elements in power electronic circuits. The switches used in power electronic converters can be categorized as uncontrolled, semi-controlled, and fully controlled switches. We'll learn about the switch categories one by one, each followed by the discussion on the circuits in which a category of switches is used. In module 2.1, uncontrolled switches are discussed, and module 2.2, rectifier circuits using the uncontrolled switches are discussed. Rectifier is a circuit that converts AC voltage, single phase or three phase, to DC. Module 3 deals with semi-controlled switches and phase controlled rectifiers which employ the semi-controlled switches. Module 4 is devoted to fully controlled switches. Power electronic converters used to convert one level of DC voltage to the other. The DC-DC converters are discussed in module 5. Finally, we'll learn about inverters in module 6, which can convert DC to single phase or three phase AC. Thank you.